Hello, this is Dr. Azevek, and I'd like to welcome you back to our course Introduction to Reinforcement Learning, Motion Control. The subject of our lecture is futuristic reinforcement learning system blocks. What we see over here is the example taken from MATLAB, one of the best ways to get started learning reinforcement learning motion control. And what is shown here is a block diagram of Cadbrook walking robot example. We see the robot over here, very similar to what Boston Dynamics is building. The robot is the system, very similar to what we had before, seen in a PID, the state. The state had 1 degree of freedom, and the robot over here has 8 degrees of freedom, where each degree of freedom has motor torque. Over here, we had only 1. In the PID, we had the controller over here, and we see the neural network controller over here in the reinforcement learning. In a PID, we had position feedback for 1 degree of freedom. And over here, we have 44 observations from the robot, which are being fed back into the neural network, and they call the CG position, the roll, pitch, and yaw, the XYZ position, the XYZ velocity, the friction, and the normal forces at the legs, and the torque to the joints. All of this is being fed back. They are partly going into the observation and partly going into the reward function. Extremely important to realize that the difference between the PID and the reinforcement learning is that in a PID, we set up the reference point that we like it to move, and that's what the PID is making the output to do. Over here, we set up the reference, but they may be due to observed variables of the environment. There may be different ways of acting. And what we like the neural record to do with not only 3 parameters, but with hundreds of parameters, as we saw earlier, is to come up with the best option of motion that it could do with its degrees of freedom. The reward function in this particular case was shown to be related to velocity, time, the height of the torso, the angle, and the torque. What we see over here, this is the function. The higher velocity, the higher the reward. The shorter the time it takes to complete the job, the higher the reward. But if the height is getting low, then the reward is negative. It's like a penalty. And then if the angle is disturbed, then there is over here a penalty on the angle. And then if the torque, too much torque over here, in order to make the motion is also a penalty. So this is the reward function. And any specific application, custom application of a standard device, this could be a standard device, but it may have different application and tasks. The reward function will be different. And reinforcement learning actually allows us to train the system, as Boston Dynamics CEO mentioned, in much shorter time that we would do it with previous systems. The episode in the training process, they're trying to optimize the neural network parameters, will end when the height is too low of the head, the tail, and also the torso. When the knees are below the ground, meaning that the robot actually fell down, and when the roll, pitch, and yaw are outside the maximum value that allowed to do. during the training process, what we see over here, again, in a MATLAB with a particular agent, DDPG, and what we'll see when we run it, we'll see the motion of the robot when he falls down and gets up and try again and again and again in the episode. And we see that over here we've seen 4,000 episodes. Now, unlike PID, that you can tune the machine with 3 parameters right on the machine itself without destroying it, it will not make sense to train the machine 4,000 times. If the time consuming every time it falls, it actually may be damaged. So what we see over here is in a learning process simulation. We see over here the total reward, and we see as after each iteration, the system is learning and is coming up with a higher reward. And it stops when the total reward of the entire process is shown over here in blue line. This is the average, but you see that in each episode, it actually could be very low, it could be very high. This is when the robot is falling down and getting up, is converging to another estimate. And we'll see later on when we talk, let's take a look at the details, that this could be the actual of the agent, and this could be the critic of the agent. So the critic gives the total estimate of the total reward that the system may have, and the actual actually also doing the same thing, but it uses the actual rewards after each iteration. And when they converge, then that's basically the end of the training system. And when the training system is completed, then the neural network parameter with matrix operations, so-called TensorFlow, will go inside the controller, which is going to be a hardware, and it will actually run modelless, exactly like the PID. There'll be a controller, there'll be all these feedbacks that come into the controller. There will not be any reward function or any modeling or any observations anymore. It'll simply be the multiplication of all these sensor signals times the weight of the neural network, and the output will be the motor torques. With that, I'd like to thank you for listening, and I look forward to see you in our next lesson. Thank you.